Hello, my name is Younghyun Kim. I'm a master in Korea Advanced Institute of Science and Technology. In this video, I'm going to present our work MS-UDA, Multispectral Unsupervised Domain Adaptation for Summer Image Semantic Segmentation. Recently, semantic segmentation has been emphasized for high levels in understanding. Unlike conventional RGB image-based semantic segmentation tasks, what it focuses on is summer sensor image. The RGB images have clear boundary and sufficient texture under well-lit condition. However, the sensor failure can be easily occurred by light conditions such as glare or low light condition. In contrast, the summer camera has high roughness to light condition. Furthermore, the summer sensor excels at capturing heat sources such as human, driving car, and animals, which are very important objects for scene understanding for autonomous driving. However, there are some reasons why this brilliant sensor has not been used for semantic segmentation. First, the image captured by summer sensor has low resolution, textureless, and colorless features. Second, the summer image segmentation dataset is tremendously scarce compared with RGB segmentation dataset. For the first reason, the previous researchers have tried sensor fusion. They have expected that the benefits of each sensor can compensate the sensor intrinsic shortcomings. However, we could find the results against the expectation. As you can see in the right side, sensor failure from one sensor actually hindered the whole inference. More importantly, when using multi-sensor system, it is easy to have a spatial or temporal misalignment problem. Therefore, we think sensor fusion is not the only solution to utilize summer sensor. The second problem is about data scarcity problem. Unsupervised domain adaptation, or UDA, is an efficient method to solve data scarcity problem. UDA transfers task-specific knowledge from the source domain, which has labels, to target domain, which has no labels. Previous UDA transfers knowledge between same sensor modalities such as RGB and RGB or same multi-sensor domains. It has never tackled data scarcity in non-RGB dataset itself. In contrast, we assumed multispectral domain adaptation can tackle the data scarcity in summer domain by knowledge transfer from RGB domain to different sensor domain. RGB domain has enough labeled dataset to be source domain. Also, it has superior segmentation performance due to sufficient features under well-lit condition. The idea of MS-UDA is to take only these advantages of RGB domain to solve data scarcity problem and improve task performance at the same time. However, this new methodology is expected to encounter some challenges. There should be a larger gap between different sensor modalities compared with the gap between same sensor modality. Therefore, domain alignment method using adversarial learning in conventional UDA is not enough for multispectral domain adaptation. Also, we do not use any ground truth even for source domain, so we should consider pseudo-label generation together. To solve these challenges, first, we utilize independent encoders for different sensor properties to handle the large gap between sensor domains. Also, we set paired RGB and summer images as source and target domain, respectively, to transfer knowledge from RGB to summer domain with consistency loss. Furthermore, we use a high-performance segmentation network pre-trained on large-scale dataset. The idea is very clear. The source RGB domain learns segmentation from large-scale RGB dataset. Then, it transfers this knowledge to target summer domain by domain adaptation. This is the whole pipeline of proposed MS-UDA methodology. This is the RGB stream of MS-UDA. It consists of RGB-specific encoder and shared decoder. The separate encoder of RGB stream concentrates on learning segmentation with the knowledge from high-performance segmentation network. The summer encoder enforces summer stream to predict source-like segmentation with consistency loss between RGB prediction and summer prediction, and competition with discriminator. The shared decoder for RGB stream learns high-performance segmentation and For summer stream, it mimicked the source domain using parameter sharing, consistency loss, and adversarial learning. Also, the shared decoder works to help sensor-specific encoder find shared feature space by working as common propagation paths of loss constraints. Discriminator distinguishes whether its input, here prediction result, is from RGB stream or summer stream. Discriminator competes with segmentation network, and this helps summer stream mimic RGB stream. Since MS-UDA receives RGB segmentation knowledge under valid condition, their input dataset basically does not include nighttime dataset. To reduce intra-domain gap between day and night in summer domain, we utilized cyclic-based image translation to make fake nighttime summer images. These are the experiments we did. These are the dataset we used. We utilized the previous RGBT dataset, MF dataset, which has 8 classes. To validate our methodology, we make new segmentation dataset, Kai's pedestrian dataset, or KP dataset. This is based on Kai's pedestrian detection dataset. It has a cityscape style 19 classes. All training is done in daytime, and the test is done in nighttime. First, these are the qualitative results on MF dataset. Ours shows better results compared with supervised ones. We can see the same tendency on KP dataset. The first experiment is a comparison with RGBT benchmark MF day night dataset. Our MS-UDA is trained on only daytime and infer the prediction with monomodality, but it shows comparable or even better results compared with supervised network. This demonstrates that multispectral unsupervised domain adaptation is as much effective as RGBT fusion network. The second experiment is to show why MS-UDA is proposed. In this experiment, all of the networks use technically the same baseline but are trained in different methods. We compare 3 methods. First, supervised network. Second, self-trained network supervised with pseudo-labels. Third, summer stream of our MS-UDA. This comparison will show the effectiveness of MS-UDA methodology. As a result, MS-UDA achieved the best performance among 3 methods. From this experiment, we can find a clear limitation of sensor fusion. Large gap between day and night in RGB images hinder the inference, so the RGBT fusion supervised network degrades the performance. Our MS-UDA outperforms self-trained network and also supervised network. This demonstrates one of our assumptions. Domain adaptation from RGB domain can improve the segmentation performance for target summer domain. Also, pixel level adaptation for learning nighttime representation improves performance. Therefore, our final model consists of multispectral domain adaptation and pixel level adaptation. The third experiment is about architecture design. One of the expected challenges of multispectral UDA is larger gap between source and target domain. To solve this challenge, we used separate encoders for RGB stream and summer stream. Under same loss constraints, we compare fully shared, fully separate, and decoder shared architectures. As a result, decoder shared architecture achieved the best performance. This is because only decoder shared architecture can take segmentation knowledge by parameter sharing and find shared feature space with sensor-specific encoders to consider the sensor properties at the same time. Fully shared architecture, which is commonly used in conventional UDA, was not suitable for multispectral UDA or sensor-to-sensor domain adaptation. 2 sensor domains are too different for a network to learn with stability. Fully separate architecture, however, can consider sensor-specific properties, but it cannot take advantages of semantic knowledge from RGB domain in network level. This means only sensor-specific encoder and shared decoder architecture overcomes the challenges, so it is suitable for sensor-to-sensor domain adaptation. As mentioned before, we claimed even different encoders can find shared feature space. This is because the loss is propagated through a shared decoder. Let's see the TSNE visualization of features from each encoder. When the network is trained with each modality individually, the features from both domains have discrete distribution. However, in MS-UDA, features from RGB and summer domains have similar distribution. Furthermore, we compare low-level features from the first layer of encoder and high-level features from the last layer of encoder. TSNE visualization shows that features from both domains are getting closer through separate encoders. The fourth experiment is to find a way to reduce intra-domain gap between daytime and nighttime in summer domain. We compare pixel-level adaptation, half contrast, and day-to-night UDA cases. We find that day-to-night UDA loses RGB guidance and degrades the performance. Also, the nighttime representation of summer dataset is not simply represented like half contrast. Day-to-night image translation or pixel-level adaptation enforced summer stream to learn nighttime representation, thus it achieved the best performance. These are the result videos. Let's watch the campus scenes. To summarize, we proposed MS-UDA methodology to solve challenges in summer image semantic segmentation task. Summer image semantic segmentation for driving scenes was hardly explored due to its deficient features and deficient dataset. MS-UDA utilizes domain adaptation from RGB domain to summer domain to solve data scarcity problem and low segmentation performance on summer domain. So, our contributions are: first, we solved data scarcity problem in summer image dataset. Second, even without ground truth, we improved the performance compared with supervised networks. Third, we first proposed sensor-to-sensor domain adaptation framework for semantic segmentation. Fourth, we proposed new RGBT semantic segmentation dataset. This is the end of the presentation. Thank you for your listening to the presentation. If you have any question later, please contact us by the email below. Thank you very much.